Okay. Like I said, I'm going to kick the deadline back for the assembler because of the Moodle problem. So the assembler is now due at 5 p.m. Friday. Okay. This is entirely due to the Moodle problems. Nevertheless, if some issues arise, by all means, make an appointment with me tomorrow. I'll be happy to help you. I know exams are really stressful, so they're graded. I got them for you today. I'm going to pass these back, and then I'll spend a little time going over it. Yeah, your answer on that one was really, really bad.
Yeah. Oh.
Yes. Here. All right, so let's talk about these. On every question, at least one person got full credit. And typically more than one. First question, draw a truth table for an OR gate, create a circuit that implements an OR gate using only NAND gates. So. Basically looks like that. A number of people messed this up by implementing AND instead of OR. That was a common problem. Second problem, truth table for a two-way demultiplexer. Create a circuit that implements a demultiplexer using AND or not. So truth table is something like this. Just review this briefly. In a demultiplexer, you're determining to which output you want to route your input. So if the input is 0, all outputs are zeros. Okay. This came up more than a few times, actually. Demultiplexer, if there's no input, there's no output. Now, if there is an input, a selective 0 routes it to A, selective 1 routes it to B. Inevitably, with every problem involving a demultiplexer or multiplexer, more than one person inevitably mixed the two up. So it's important to be very clear in your head what multiplexing is and what demultiplexing is, okay? All right. Problem 3 is just using the demultiplexers that are two-way go four-way. So there were a number of solutions where inadvertently they involved multiplexers. So use the first select bit to choose which second level demultiplexer you're going to employ. Then use the other select bit equally on both of those guys. Have something like A, B, C, or D. Key concept here is, again, if you've got a 0 input coming into a demultiplexer, all the outputs are 0. That's what lets this work. Okay. For an 8-byte RAM chip, describe the following. All right, so there were a lot of problems on this one. Generally speaking, what kind of thing was I looking for? So to read a memory location, I wanted you to specify the address goes into a multiplexer select bits. Okay. Mention that the multiplexer needs to have a number of select bits equal to the number of bits in the address. All 8 memory locations are the inputs. The output is based on the select bits, in other words, the address. For writing, you use an 8-way demultiplexer to pick where the load bit is activated. So it's not going to write if there's no write bit coming in. So the write input for the chip goes into the demultiplexer. The select bits are based on the address. And then the outputs are wired to the 8 load bits on the registers. So if there's no 0 coming in, load bits on the registers are all going to be 0. Right. There's a 1 coming in, exactly one of them will be a 1. And that's the address that gets written. 5 and 6. 5 was the half adder, 6 was the full adder. Most of you did pretty well on these. I mean, inevitably there were a couple people that were like, what operation is performed? Well, it's like a bunch of ands and ors. Oh, which wasn't like wrong as such, but not really getting at the heart of it. And so I typically took a point off for that. Solution on number 6. I mean, let's face it. If you use 2 half adders and an OR gate, that one's pretty clean. I probably deserved the few that I got that were not like that. Number 7. Those were fascinating to grade. Oh. Oh man. Yeah. Yeah. Those were fun. Number 7. How is 2's complement calculated? It's 2 steps, right? You're going to invert all bits. Then you add 1. Illustrate the process with an example. Any example would do. I just wanted you to give me a number, like say 0101, invert the bits, add 1, and then claim, aha, we now have the negated number. Second part, why is it important? Illustrate with an example. It's important because it lets you subtract by adding a negative number. And so then I just wanted you to give me a subtraction. So you could say, oh, how about 2 minus 1? So you take the 2, put it in binary, do a -1, so you do the complementing and everything, bam, 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 bam. Add them up. Oops, that's 0. And then what do you know? 2 minus 1 is 1. So really, any pair of small integers would have done very nicely there. What circuits are wired to the system clock? Why? All memory circuits are wired to the system clock. In general, if you seem to somehow have the idea, I give you credit for this. So some of you attempted like an extremely comprehensive list of every memory circuit ever, which was fine. You clearly understood what was going on. Others of you just referenced a couple of things, but clearly there were the things that were most directly important, like you didn't mention D flip-flop, but you talked about registers or whatever. You know, and that was all fine. Basically, I was just kind of looking. Tell me memory. If you said the ALU needed the clock, that was a problem. Okay. And for example, because the ALU doesn't need a clock. wired the system clock to ensure synchronized updates to memory. There were lots of ways to say that. Some of them made total sense to me and got full credit. Others made less sense to me and got less credit. If your particular answer you think gets the synchronized update idea across, and in my grading I did not seem to agree with you, I am more than happy to have a conversation with you about where it's coming from and adjust the points if necessary. 9, explain the process by which a CPU executes these two things. All right, these were not good questions in that I did not make absolutely clear what I was looking for. And so some of the answers I found disappointing, but reasonable interpretations of the question. What I was looking for was essentially, what does the decoding process look like? So if you look at 9.1, what I'm looking for is something like the following. Stuff goes through the ALU. The ALU has condition bits, which then get matched up with the appropriate J bits in the instruction, right? So for instance, if you're jumping on negative, there's a J bit for that. That gets ANDed with that negative flag. If that's a 1, you're going to jump. And then you got to OR all those guys together. If any of those are up, you jump. Okay? And then the other really crucial thing I was looking for was, if it just sort of said, and then it jumps, I didn't really like that. I wanted you to say, the program counter's value is replaced by the contents of the address register. Okay? There were a few things that weren't quite that, but I felt like kind of got the idea across. I got full credit. But in general, I didn't award as much credit for answers that had the feel of, well, then the magic happens and it jumps. And I felt like there were a good number of those, which weren't really what I was looking for. For the ALU instruction, 1 operand register, 1 in RAM, results stored back to RAM. What I was really looking for here was route the bits from the instruction to the C bits of the ALU. Note that the A bit would have to be a 1 because the operands are memory, okay, as opposed to A. And then I was looking for something that indicated that you have to tell RAM you're going to write. So the output of the ALU needs to be fed to the input of the RAM. The address register needs to be routed to the RAM. And then there's a write bit on the RAM saying you're going to write. And I wanted to see something that showed that you understood that. Again, in retrospect, I wasn't real happy with the question. I would have said something about explain the process by which a CPU decodes to really emphasize I'm looking for how do the bits in the instruction cause something to happen. Okay. I tried to be generous. I'll be open to negotiations on some of those problems if you feel like your answer was a reasonable interpretation of the question and I maybe penalized it unfairly. Open to negotiations, no guarantees. Okay, I do want to emphasize that. 10, difference between assembly and machine language. Most of you got this. If it's assembly language, it's written in some kind of alphanumeric, symbolic code that's more human readable. Machine language instruction, 1s and 0s. Why is that? The symbols are easy for a human to read, but the 1s and 0s are what makes something happen in a circuit. Okay? In what ways are they alike? One-to-one correspondence between the instructions. Every assembly language instruction is exactly one machine language instruction and vice versa. So in general, words to that effect, I tried to give full credit. 11 and 12, these were mostly pretty good. There were a few common problems. On 11, it was pretty common for people to like write the code for the if correctly and then just fall into the else and do that too. So it just fall through. That was a point off. That happened a lot. What you needed was a label after all of that that you could dump to, okay? And that is what illustrates that the code isn't getting munched together. These were kind of hit or miss. Like some of you knew the assembly language super well and delivered extremely clean solutions. Others of you had trouble remembering some details. Like there were some attempts to do put like a value in memory. Well, unless that value is 0, 1, or -1, you can't do that. Sometimes people try to do stuff like m plus m. Well, again, the CPU doesn't actually support that. You know, it's understandable how you might do that. Sometimes people were confused about how jumps happen. So the load the A register with the jump address would come after the jump instruction. That actually was an issue in the earlier problem as well about the jump decoding. A number of people said, well, then it jumps to where the destination bits say. No, actually it doesn't. It depends on the A register. Okay. So that was a bit of a problem. Yeah, 12 in general was a little better than 11. The biggest problem on 12 was like sticking like a 170 directly into memory, which doesn't work. And that sort of thing. Okay. So that was a test. For the most part, people did pretty well. I thought it was a reasonably challenging test. If you got an A or a B on this, you know the material pretty well, aside from maybe a small couple gaps. Okay. You got not in the 70s on it. You know, you're doing okay, but there are definitely a couple issues where you really need some review. You need to go over stuff. For anybody, I'm more than happy to walk through the test with you and talk about, okay, this is where you seem to be running aground. How might we make our way forward from here? Okay. Below 70, there is some problems, and we may need to talk about strategically how can you do better in the class. Okay. And so, especially if you were below 70, make an appointment with me. Let's talk and let's see what we can do to get you in a better situation. Okay. I genuinely want everybody to succeed in the class, and I think it's possible to do. And so, if there's some roadblocks, I'm ready to have a conversation about that and seeing what we can do to make our way forward. Okay. But yeah, the test was entirely possible. Like I said, 5 of you got A's and did very, very well. High grade was a 99. So none of them were perfect, but generally quite good. So that's enough about the test for now. If you got questions, I want you to follow up with me individually. I'd rather not A, spend more class time on it, and B, spend like class time going over particulars of a solution quite individual to you. But in my office, I am more than happy to go through the test with you in whatever detail, talk about how it was graded, talk about what was going on, what happened. All good? All right. All right. So we're ready to start talking about chapter 7. Virtual machines. So a virtual machine is like a level of code that is in between a high-level language and a machine language. It looks like a high-level machine language for the most part. Major goal of all virtual machines is to try to be hardware independent. So the idea is you write a compiler for a high-level language that generates virtual machine code. Then you've got some kind of code generator that's specialized in transforming that virtual machine code to the code of a particular hardware architecture. In this light, I do want to spend a couple of moments talking about, in contemporary practice, what the relevance of this actually is. So, let's talk about CPUs for a moment. There are two extremely widespread major instruction set architectures in use. Oops. Okay. Anybody know what they are? Thoughts? Top of your heads? Okay. There are two major machine languages in use in contemporary machines. There are two major ones in use. Yeah, Nick.
C++.
No, that's a language. Yeah. I'm talking like machine languages. C++ is a high-level one. We're talking machine language. There are two major machine languages in use. Just wondering if you all have heard of them. I'll talk about them.
Is Linux, or like what Linux is written in, is that one of them? I can't remember what it's called.
Yeah, so Linux, so that's an operating system.
Yeah.
And like most operating systems, it's written in the C language.
Okay.
So C is actually a somewhat high-level language.
Okay.
It's definitely not a machine language. Yeah.
Excellent.
Oh. So let me just tell you, I think quite understood. So first major machine language, it's called x86. This is the machine language used by Intel. Okay. Let's think about this for a minute. Intel Corporation is the single biggest manufacturer of CPUs on the planet. They have had a dominant position in the manufacturing of CPUs since about 1982 or thereabouts. The first IBM personal computer had the Intel 8088, which was then supplanted by the 8086. That's where this 86 comes from in the X. From there, Intel continued to develop the architecture. The next major chip was the 8286, and then was the 8386. Next one, any guesses? Yeah. How about the next one? Any guesses? It was, in fact, the 586, but their marketing people didn't call it that anymore. This they called the Pentium. Why Pentium? Because of the 5. The Pentium was a massive, massive bestseller and quite an effective chip, aside from an amusing controversy over its floating point unit that was common at the time. Like there was a bug in the floating point unit that caused all kinds of problems, and it was like in millions of PCs. And the thing is, if you got a bug in the math routine on your CPU, you can't just download a software patch or like you just can't fix it. So that around 1995, this was sort of a major source of entertainment for people that think this sort of thing is funny. Here. Now here's the thing, right? So I'm listing all these numbers. That doesn't really mean a whole lot, right? But here's the kicker. If you write a machine language program that runs on the 8088, that exact same program in terms of the bit layout will run on a Pentium or anything else. So Intel put forward a tremendous amount of effort to make sure that if you have some favorite DOS game from 1985, it'll still run on a Windows 10 machine. Dang. Like, that's not just Intel, that's Microsoft also. Microsoft makes sure that all versions of Windows are backwards compatible all the way down. So, Intel's the first major family.
Is the upper family ARM?
ARM. ARM is the other. ARM is not typically found in PCs. But if it's not a PC and it's a computer, you better believe it's running an ARM chip. What do I mean, for example? How about smartphones? How about Raspberry Pi? All those sorts of things. Lego Mindstorms. Your toaster. If your toaster has a CPU, it's from ARM. So how did ARM get a market niche? ARM specialized in coming up with a machine instruction architecture with relatively low power consumption. Let's think about some of the implications of this. So if you've got a nice desktop machine and it's plugged into the wall, if you're paying, I don't know, $1 a day, $2 a day for electricity, in the end, you probably just don't care very much. Like, computers can use a fair amount of juice, but your air conditioner probably uses a lot more, for example. You just plug it in, let it drain the electricity it needs to drain. It does your favorite 3D rendered game, and life is good. Right. The same. Now, on the other hand, when you're talking about small devices, these are all running off batteries. And the less power you drain, the longer your battery life's going to be. Also, the less power you drain, the less heat you have to dissipate from the unit. I mean, I think we've all had those moments, right, where we're doing something or other on our smartphone. Maybe we're just playing Tetris really awesomely, and the thing gets hot, which is kind of uncomfortable. Kind of stinks to like try to play Tetris doing that. Just sort of getting it on the edge with your fingertips. The trouble is, the more juice it uses, it's got to dissipate the heat. That's physics. That's entropy. That's like, deal with it. So the point is, if you can reduce your power consumption, you have a much more usable device. And so ARM is based on a very different series of trade-offs than the Intel designs. Furthermore, the Intel designs were undertaken at a time when people routinely wrote programs in machine language. Like, they would actually use a programming language. That almost never happens anymore. At this point, most of the assembly language that gets written by compiler writers, which this week is what you will be. That's just the way it tends to proceed. You figure out, okay, for a given virtual machine, how can you most efficiently map that into the instruction set architecture of the target device? Now, because virtual machine architectures are relatively close to a machine language, it's often much easier to define a mapping between that and the machine language than a mapping done directly from the high-level language. So every major language translation system does this sort of thing, okay? So what are some examples? One example is a compiler family based on what's called LLVM, low-level virtual machine. Really clever name, right? This was financed largely by Apple. And for many, many, many languages, what you do is compile to LLVM, and then from there, that goes into either Intel or ARM. Okay? One of those two directions. What are some other examples? JVM. This is the Java virtual machine. Now, this is a little bit different than what goes on with LLVM. LLVM is a component of a compiler system. So the idea is you take your high-level program, crank up the compiler, and it cranks out machine code. That's about what we're going to be doing, by the way. JVM is doing something different. This is actually an interpreter for the virtual machine language. So in a language like Java, the compiler takes your Java code and generates JVM instructions. That's what goes in the .class files. At runtime, the Java virtual machine fires up and is actually an interpreter for the JVM language. Now you might wonder, if Java does that, how do they get it to run fast? And JVM does some pretty clever stuff. Namely, what's called just-in-time compiling. So, Java Virtual Machine does amazing things at runtime. At runtime, it will profile the program, identify tight loops that get repeated a lot, and then on the fly as the program is running, translate the pertinent virtual machine code directly into machine language. For some things, this is great. If you write, say, a web server in Java, that's awesome. Why is that? Because you leave the thing running for days. The Java virtual machine can develop a pretty good profile of its execution and heavily optimize and target the compiling to take into account these runtime characteristics. Dang. I mean, you can do some great stuff with that. For other things, it doesn't work so well. Stuff that's kind of one-shot, run and done, it's less effective as a tactic. Python also has a virtual machine under it, and that is pretty strictly an interpreter. So when you start a Python program, like just running a Python program, as you run it, it'll transform it into VM, and that VM gets interpreted. That's what Python does. Now, what all of these things have in common is that in practice, nobody actually directly generates machine code. You always generate a virtual machine level first, and then you deal from that to the machine code. For the next few weeks, that's what we're going to be doing. Chapter 7 is translating the first part of the virtual machine code. Chapter 8 is the second part. Chapter 8 actually gets kind of complex, and so I'm actually going to have 2 different deadlines for Chapter 8. There'll be a first deadline to get some of the easier test cases going, and then a second deadline to get the rest of it working. Okay, and I will be having you submit those separately, and I'll be grading them separately. So this week, we're just looking at level 1. So all of this was just to contextualize what we're doing, why we're doing it, and what kind of contemporary relevance it has. Any questions on any of this stuff before we start looking at some details? Calvin.
So is this just like take assembly language out of the picture?
So this time, yeah, it really does, because we're going to write this VM to assembly translator, and at this point, we're basically done with assembly. Now, in certain languages, especially in the C family, sometimes people are like, well, I really want this subroutine to be an assembly, and they'll do stuff like that. In practice, that's not useful all that often. A really good compiler can generate optimized assembly code that's as good as what anybody will handwrite, except for, like, you know, super duper programmers. And so it is not typically worth the time investment. But certainly in terms of what we're doing, after project 8, we are done with assembly language. Other questions so far? Okay. So what is it like? What is virtual machine code like? So the virtual machine imposes the following kinds of abstractions. In particular, it's going to provide memory abstraction. So within the context of the virtual machine, we no longer deal in a direct way with memory addresses in the computer. Everything becomes indirect. The key memory abstraction that we're going to deal with is called a segment. So the idea is that the virtual machine says, these are the memory segments you have. You deal with them in terms of offsets in various ways. And then the virtual machine system takes care of mapping those segments to actual addresses in RAM. Okay? And that's how that proceeds. That's how it proceeds. So what are some of these segments like? Funny you asked. So in this project, for the architecture of the system that we're developing, page 131 of your book gives a nice overview. And I'm going to talk about them for a bit. The first segment is called argument. What's the idea of argument? So stores, oh man, can't write today. Let me try that again. Args for a function. So every function actually has, so functions are a big part of the virtual machine. So the virtual machine is going to give us functions, named functions, which is a huge boost in abstraction over what we get in machine language. Functions are your friend. Okay. So the virtual machine code has a concept of the current function that we're in. We're going to talk over the next few class periods about how it forms that concept. And for now, take it for granted. We've got a notion of the current function we're in. And then with all of these segments, you say, I'm going to be in the argument segment. And then you give a number from 0 to n minus 1. N is the number of arguments. So if you want to talk about the first argument, use the 0 offset. The second argument is the 1 offset, and so forth. And the virtual machine translator will then have generated assembly code that takes all these offsets into account. Okay. Now you can see, though, already that this is the kind of abstraction that makes it a lot easier to think about how to translate your high-level language. So it really comes down to is, whatever your high-level language gives you, if you can turn the thing into functions, you can then reference the arguments using these segments, and how this turns into a memory map for the architecture is no longer your problem. And that makes life a lot easier, actually. Okay. Next segment is local. So these are local variables for a function. And so this might seem pretty similar to argument, but this is really concerned about the variables that are declared within a function. Now, what's the difference here? Argument, in the end, is going to need to be accessed by whoever calls the function because it has to send the arguments. Local is something that only the function itself is going to deal with. And that's why those are distinct segments of memory. Okay. Next is a segment called static. And in practice, these are going to be global variables in the program. Now, the way that this virtual machine stuff works for what we're doing, there are no true global variables. That is to say, we're actually going to be able to take multiple virtual machine files and stitch them together into a single assembly language program. To do this, within a given virtual machine file, only the static variables that are local to that file are visible to it. So there are no true global variables that span across virtual machine files. Ultimately, for assembly language, of course, everything is global because it's just a memory location. In general, global variables that are truly global across a high-level program are a common source of bugs, and people like to avoid them. Still, sometimes there's not much alternative. Next segment is called constant. And this is not a real segment. So what do I mean by this? the purpose of constant is to provide a way of accessing specific integer values within your program. But by having this idea of segment and offset, it means we can have a uniform syntax for the virtual machine instructions. So if you always talk about a value in terms of what segment is it in and what's the offset, you can talk about constants by saying, I'm in the constant segment, and the offset is just the constant you want. So for example, let's say you want to load 100, you want to do something with the number 100. Well, you can just access the constant segment, and then say my offset is 100. And that gets me the value 100, which I can then use however I want. There are two segments which are called this and that. These are for what is called heap manipulation. And we're going to kick that can down the road for now. We'll come back to talking about those guys later. Pointer actually changes this and that. So in a way, you can think of this and that as general pointers in the memory, and then pointer changes what they point to. And then finally, there's the temp segment. This is just 8 free locations with which you can do whatever you want. So these tend to be useful once you start working on the compiler and they're just values you just need to stash somewhere for a moment. Then the temp segment comes in handy. So typically that figures in as part of the implementation of something. Now, what all memory accesses have in common in the scheme is they look something like this. So you've got some kind of operation. And we're going to talk about what those look like in just a moment. Then you have the segment and the offset. So these ultimately turn into an address where you then do your work. This syntax, or this sketch of a syntax, is applicable for both reading and writing. Some operations will be memory reads, and so they will go to memory, retrieve a value, and then put it somewhere mysterious we'll talk about in just a moment. Memory writes will take a value from this mysterious place and store it in memory as you specify. You know what kind of values are we ultimately talking about? There is only one data type in the virtual machine language, which I am sure you will be shocked to know, and that this data type is a 16-bit integer. Now, this 16-bit integer can also be thought of as a Boolean. Well, how's that going to work? False is 0. True is -1. False is 0 and true is -1. Why is true -1? Because if it's -1, every bit is a 1. That means if you not the location, if you not and it's all 1s, you get all 0s. False. If you not, you're all 0s, you get all 1s. True. So this is admittedly mildly awkward, the -1 business, but it works pretty cleanly in practice. Okay. So any questions so far? I'm going to talk shortly about what these operations are for memory access. This idea of segments makes sense so far? Okay. So what are the operations? So I need to emphasize here, this virtual machine is what is called a stack machine. This virtual machine relies heavily on the idea that there is this single means of information interchange in the system, and that is using a stack. Those of you that have taken the data structures class may well remember dealing with stacks at some point. But let's review what the data structure is. So stack is a data structure which is called last in, first out, or LIFO. So stacks in particular have two key operations, push and pop. So push some value, puts it on the top of the stack. Pop removes the top value. Where stacks get really, really useful in the context we're thinking about is actually for arithmetic. Let me show you what I mean. Let's take an expression, something like the following. 4 plus 3 times 5. A stack arithmetic operation does the following. Push, or I'm sorry, wait a minute. Pop top two values, add them, or whatever. Yeah. So subtraction, whatever, multiplication, division. Push result onto the stack. So what's this wind up looking like? So let's take something like 4 plus 3 times 5. So here's what you would do. Here's the bottom of the stack. So first you push the 4 onto the stack. Then you push the 3. Then you push the 5. Now you do a multiplication instruction. You pop these two guys off the stack. So you pop 5 and 3 and multiply them. And now you push the result onto the stack, which is 15. Having done this, you now do addition. That pops 15 and 4 off the stack and replaces it with 19, which now remains on the stack. What's really nice about this scheme is that it gives an extremely unambiguous ordering for arithmetic operations. In fact, any algebraic expression can be transformed into a series of stack-based operations with identical semantics. What's nice about this is stacks are extremely easy to implement in terms of machine language and low-level hardware. In the deeper past, when machine languages were actually commonly used in practice, the machine language itself would have stack instructions. I know I keep bringing it up, but the Commodore 64 was an excellent example of this. So the Commodore 64 had a hardware-implemented stack. So within the machine language itself, you could go to subroutines. You could actually define functions in the machine language. That's not so common anymore. Like in ARM, forget it. Although ARM has some really clever ways around that. The point is, yeah, you can actually do this in hardware in pure circuitry. You know, you could design a CPU that runs its own stack. I've done it before. It's kind of a fun exercise. That said, you know, if you can do it in a circuit, doing it in software isn't really so hard. What's the key to implementing a stack? basically, to implement a stack, you need two things. You need what's called a stack pointer, and you need a bunch of memory. Okay? So, how does this work, basically? So, imagine you've got a region of memory dedicated to your stack. Let's go ahead and talk about it in terms of a virtual machine. Okay? Your virtual machine, the stack is going to begin at location 256, and it actually ends at 2047. Okay. So initially, the stack pointer, so we're actually going to use memory location 0 on the computer to store the stack pointer. The stack pointer initially is going to be 256. So whenever you do a push, what you do is you store a value at whatever address the stack pointer is at, and then you increment the stack pointer by 1. So push 1, store 2, increment. For a pop, you have to very carefully do this in the reverse order. First, you're going to decrement the stack pointer, and then 2, retrieve a value. Okay? So, almost goes without saying, you better get these down cold or your virtual machine is sunk. Okay? You need to have pretty reliable pushing and popping code that you're generating in your assembly language. It's not really hard to do this, right? You know, you get the value at 0 into the address register, and then you just go to town on memory. Keep in mind, the ALU itself can add 1 and subtract 1 directly as you need it. So those add 1s and subtract 1s are really essential for an efficient implementation of the stack pointer. And if everything goes through the stack, and it basically will, fast stack pointer updates are essential for efficient code. So, in terms of the assembly, that's ultimately how you're going to implement it. Now, I've wondered what happens if you go past 2047. And that, of course, is stack overflow, which is very, very bad. What most high-level languages do is if they detect a stack overflow, they crash the program. I'm seeing some knowing gazes of recognition on your faces as I mention this. You know, so Java will throw an exception, Python will throw an exception very happily. C will ignore it and overwrite the rest of memory. Well, you know, you got to get your buffer overflow attacks from somewhere. Anyway, that's a bit of a side issue. Maybe we'll talk about that once we in a later class. The point is, stack overflow is a bad thing. It's ultimately the job of the high-level system to detect it. You're not going to have to worry about that. You're just going to assume that all the stack manipulation is legit, okay? And it just doesn't happen to ever go that far. So we're just going to sort of put ourselves in a happy place there for the purposes of this assignment. So having said all of this, we can now go back to this issue of what these operations are. You may have already guessed. They are push and pop. So those are your first VM language instructions. Push, segment, and offset will do the following. It's going to read from RAM and push the value on the stack. Pop segment offset will store value from the stack at the segment plus the offset. Okay? So you can imagine something like the following. You have an expression, it does a bunch of math, okay? Now you want to store that value in memory, you do a pop. That value then gets placed in memory accordingly. Now where did the values come from? Well, ultimately they're either constants or they came from memory. So to set up your computation, you do the pushes to get those values on the stack so that the computation can occur. Okay. So Project 7, we've kind of hit all the main concepts at this point. For Project 7, you're going to implement a virtual machine translator that takes a virtual machine program as its input and generates an ASM file as the output. So let's talk about that a bit. So you're going to write a program called VM Translator. It's going to take some VM file as input. Then you're going to borrow the name from before the dot and generate an ASM file as output. Okay. There's an additional option, which I don't think matters very much in the first week in Project 7. It matters a lot more in Project 8. There's an additional option where instead of a VM file, you can give it a directory as the input. And then what it'll do is read all files that are in the directory and have the VM suffix. So actually read them all in and then generate a single massive ASM file that contains all the code. This turned out to be really handy later on. You're all familiar in both Java and Python with the idea of writing programs in multiple source files. So you have like a bunch of star.java files, several star.py files. Our virtual machine lets us generate a separate VM file for each source file in the source language. And so the VM's job to stitch it all together into a single cohesive program in assembly language. So let's see what some of your example inputs are going to look like, so we can use that to motivate our thoughts about the translation process. So let's start here. And dang it, where's open with when you need it? Right, can you just right click and get open? Oh, there we go. Yeah, let's set it as a notepad++. So here is a first VM program for you all to look at. Okay. This is going to push two concepts. We've got push, our segment, and our offset. So this pushes two constants onto the stack, and it then has an add instruction. So add, remember, pops the top two values from the stack, adds them, pushes the value back on the stack. Obviously, this is not a very interesting program, but it's a great first test case. So to kick this off, as this example implies, the first things you want to implement are pushing constants. Okay. Would you ever pop a constant? Does that make any sense? What do y'all think? Will we ever pop a constant?
Want to know what it is?
No, because
Okay, yeah, why not?
we're pushing a value on, that makes sense, but if we pop a value off, I I guess if we had a way to know what value it was going to be, but we only know where the this and that are going to.
Yeah. You're never going to pop a constant because constant is not actually a memory segment. It's just a way to have a uniform syntax for pushing. Okay? It just makes it easier to set up what the VM language looks like. We want to keep the syntax as simple as possible on this thing. So if you want to push a 7, you push constant 7. Pop constant 7 doesn't make any sense because it's not a real memory segment. There's nowhere to put it. Okay. So this suggests then, as you begin contemplating your implementation, implementing push constant and the arithmetic routines is of primary importance. Okay. That's the first stuff you want to test. Next, we have stack test here. So this gets a little more interesting. Now, again, you scroll through it, and it's just a push constant party. But what's it actually going to do? I have this interesting instruction called EQ. Now, what EQ is going to do is perform a comparison. Right? What comparison do you think it might be? Don't hold your breath. It's going to pop 2 values off the stack. If they are equal, it will push a true on the stack, a -1. If they are not equal, it will push a 0 on the stack, because it's false. Okay. So, you know, what the test case is going to do is it's going to push these and then be constantly checking the stack to make sure the right stuff appears on the stack. So we have a bunch of EQs. And then we get an LT. Anybody care to guess what LT is going to check? Listen, yeah. And then it's going to do GT. Any guesses on GT? No, okay. Got nothing. Got no, and then the T is the part of the acronym. Okay. Yeah. So yeah, so you got greater than going. And then there's add. We talked about add. There is also sub. So sub pops 2 values off, subtracts them, pushes the difference on. Sub is kind of subtle. Okay. What do you think makes sub subtle? Why would I say this? It's actually a little tricky to implement.
You have to make sure that you do it the right order.
You do. You do have to make sure you do it in the right order, or phrased alternatively, you have to make sure that you choose complement the correct value. And so what's the correct order? Well, there's no obvious reason to prefer one order over the other, right? Let's pause for a minute and think about what makes this a rather non-obvious issue, okay? So let's say you're doing a subtract. So you have x minus y. Then you've got your stack. Remember, this starts at 256. We typically draw the stack going downward as opposed to upward. Now, why on earth do we do that? It's because we typically draw memory going downward. You know, so address 0 is here. Address, 16384 is down here. This is a typical way to draw memory. A stack is present in memory, and so we tend to draw it according to the same kinds of conventions. So what happens is, as we push stuff on the stack, the thing that got pushed first and is at a lower memory address is our x, and the thing that got pushed second is our y. So when we perform the subtraction, it's going to be thing pushed first minus thing pushed second, okay? Now, of course, I'm telling you this knowing full well that at least one of you is going to mess this up at some point. Now, why am I saying this? Because if that person is you, I want to save you the frustration, and I want to encourage you to double check this in your solution. So if all your numbers are arithmetically inverted, this may be why. So we have sub. We have neg. Neg is kind of interesting. Neg is unary negation. It pops the top value off the stack, negates it, and pushes it right back. We also have and, or, and not. Not, like neg, is a unary operation. It pops one value off the stack, flips all the bits, pushes it back on. And or do what you think they do. Okay. Generally speaking, the implementations of all binary operations are very similar, as are all implementations of unary operations. The only difference is excuse me, the control bits to the ALU. That's the only difference. So you generate a different arithmetic instruction in all of these cases, but other than that, you're always doing the same thing. You know, I found it helpful in my solution to like have a function that would generate, say, everything I need for a binary operation. You know, so pop the first thing, pop, you know, put it somewhere, pop the second thing, put it somewhere. And then it would have a little gap where I would generate my ALU instruction. And then my template would continue. So I encourage you to think about this as you develop these and avoid not just code replication, but generated code replication. You know, if you've got a pattern that you're generating, try to just generate it in one place. And overall, I think it'll make the program go more smoothly. So let's see, anything else? So then, once you get the arithmetic going, you're going to do the memory stuff. And so basic test.vm, for example. Now this is going to start using local and this and that and temp and all those guys. Okay. So once you've got arithmetic and constants working, at that point, start worrying about your memory segments. Okay. I'm going to spend a lot of time on Tuesday talking about those. Feel free to read ahead, of course. But the basic idea is to, in some uniform way, define what those segments are. All right. And that's how those tests, generally speaking, proceed. Let me take a moment to talk about design of the system. So much as with the assembler, they provide a suggested design, okay? And their suggested design is to have a parser module and a code writer module. You can do it that way. My own preference is to create classes for each type of thing, and objects of that class then generate the appropriate code, and then they share some functions. You know, so mine is in Python. So there are a lot of possible design approaches, and maybe we'll spend some time on Tuesday talking about that. But I want to emphasize, you know, use the book's suggestions as ideas, but ultimately go with a design that is intuitive to you. Go with a design that's intuitive to you. Okay. Timetable. So this assignment is due Thursday, I think. Yeah. So today's the 29th. This will be due on Thursday the 6th. So to give you a feel for what we're doing from here, we'll start Project 8 at that point. The first part of Project 8 will be due the Tuesday before fall break starts. Then we will have fall break, and the second part will be due the Thursday after fall break. I set it up deliberately that way. I could have made it due the Tuesday after fall break, but then you would have like totally had to work on it over fall break. But making it due the Thursday after, I'm hoping it gives you a chance to have something of a break. Okay. So, you know, you might end up working on it over fall break. That's okay, but I'm genuinely trying to give you something of a break. Take that for what it's worth. And then we'll be proceeding from there. Any questions? Anything y'all want to go over in more detail that I talked about today? Yeah, Derek.
When would you use neg opposed to not?
Great question. Not simply flips all the bits. Neg performs a 2's complement. So that takes a positive number and makes it a negative number. Good question. Any other questions about what I went over today? It was a lot. I encourage you to try to get your arithmetic and constant stuff working by Tuesday. Okay? I mean, it's not necessarily going to work, but if you make that a goal, I think that will keep you on a timetable that will help you to be successful on this assignment. Okay? We're going to go over memory segments on Tuesday. Of course, feel free to start on those before then. But we're going to spend a lot of time discussing those on Tuesday. And then the final arithmetic plus total memory segmentation will be due on Thursday. So again, I encourage you to get started on it. Visit with me tomorrow or Monday if you want some help, or send me some emails as things come up. I'll see you Tuesday.